All right, let me go through some practice examples. There's plenty others in the text below this video, so make sure to work through the video. All the examples I do here are also listed there with their answers. I'll go through this quickly, as if I haven't been going through quickly as it is. Here goes. Standard question. I know, 10 people in an office, 3 needed for a committee. End of story. How many ways can that happen? What I'm really doing here, I've got 10 people, 3 are to be labelled on the committee, 7 to be labelled lucky. That's every single person has a label. That's what the labeling principle needs. Every single person to have a label. The answer must be 10 factorial, 3 labeled on, 7 labeled lucky. Self-checks, 3 plus 7 is indeed 10. That must be the actual count of ways to solve that particular problem. Classic people would call that a combination. See, I don't even know the words myself. That's a combination. I never ask myself what formula to use. Bingo, I just do it. In fact, 10 people in office, and 3 needed committee, and I added the condition. The order in which those people are chosen matters for some reason. There's some sort of ranking system going on. In which case, I would say, all right, 10 people needed office, 3 needed for committee. My labels would be chosen first as one label, chosen second as another label, chosen third as a third label, and 7 people will be labeled lucky. In which case, the answer would change to 10 factorial, chosen first, chosen second, chosen third, and lucky. I guess people call that a permutation. Again, I just do it. Most people think I'm silly for writing the 1 factorials. I actually don't think I am, because it keeps passing my self-check. In fact, people have on calculators formulas for these 2 different versions of the problem. Let it all go. That's what PNR and that's CNR or something. Obviously I don't like it. Okay, so that's it. So there are permutation combinations done without me even knowing what the difference is. Grand. More practice problems though. Suppose, say, 15 horses run a race. There'll be a first place winner, a second place winner, a third place winner. Let's assume there's no ties. How many ways could that happen? So 15 horses in a race. There's a place for first, second, and third, and there's 12 non-winners. That's a labeling problem. There must be 15 factorial, 1 labeled first, 1 labeled second, 1 labeled third, and 12 horses labeled losers. There is a way for a first, second, and third place winner in a horse race of 15 horses. Bingo. Pass my self-check. 1 plus 1 plus 1 and 12 is indeed 15. All right. Let me show you how crazy questions can get. Oh, actually, let's do something else. That's a good point. Let's do something that people wouldn't classically know what to call the problem, permutation or combination. If you think that mindset too hard. Suppose there are 100 third graders about to run a feel-good race. 50 will be called winners. So they run this race and the first 50 will be called winners. The next 30 will be called as good as winners. As good as winners. And the final 20 will be called might as well as been winners. All right. So there'll be winners, as good as winners, and might as well be winners. How many outcomes could there be to this race with 100 third graders? Well, this question's a piece of cake. It's just a labeling problem. There are going to be 100 students, of which 50 will be labeled winners, 30 will be labeled as good as winners, and 20 will be labeled might as well be winners. Bingo. There's the answer. I don't know if that's a permutation or a combination. I don't care. It just is what it is. Done. But let's do a really crazy question. Let me clean the board because it's going to take me forever just to write the question and take me about 2 seconds to answer it. So I need lots of space. All right, here is my complicated question. Goes as follows. 20 people are in an office and 2 committees are needed. Committee 1 requires 7 people, of which one person is going to be labelled chair and 2 people in that committee are going to be labelled co-secretaries. Committee 2 is going to consist of 5 people and will have 2 co-chairs and 2 co-secretaries. Let's assume no one serves on 2 committees, so no one serves twice. How many ways can I construct these 2 committees with their various chairs and co-secretaries and all the rest? Whoa. Now, in traditional methods, this will be a bit of a hassle to work this out. However, to me, it's just a labeling problem. There are 20 people. They're going to be labeled. In fact, 20 people. Let's start off the numerator. There it is. What are the possible labels? Well, let's see. 7 people are going to be on committee 1, but there's actually specialized labeling going on. One person's going to be labeled chair of committee 1. One particular labeled. 2 people are going to be co-secretaries of committee 1. So 2 people are going to be labeled co-secretaries committee 1. So 2 people get that label. And that leaves, well, that's 3 people out of 7. So I guess that leaves 4 more people going to be just ordinary committee 1 members. Ordinary committee 1. In my committee 2, there's 5 people. The special labels going on. 2 will be labeled co-chairs of committee 2. All right? 2 co-chairs of committee 2. 2 will be labeled co-secretaries. So 2 co-secretaries of committee 2. That leaves 1 person just to be an ordinary member on committee 2. Ordinary committee 2. That's 12 people have labels so far. That leaves 8 more people because there are 20 people in the office. So I guess that means 8 people are labeled lucky. Bingo. There's the answer. No work. No real hassle. Just being clear on my labels and it follows out. Absolutely gorgeous. All right, that's it. So below this video, there's a whole bunch of text. Look at that text. I've got a lot more practice examples there. Lots of fun to think about. Just think of labeling. And all that labeling really is rearranging words, and everything becomes ridiculously, obviously clear. Grand. Absolutely brilliant.